Hello everyone, welcome to this lecture 6 in the module Dielectric Properties of Insulator. In this lecture, my plan is to discuss the oriental polarization due to permanent dipole moment, right? And the permanent dipole moment, the word arises because there are some molecules. Let's say we have the HCl, right? This hydrogen chloride. The HCl molecule has a permanent dipole moment, chlorine minus ion and the hydrogen plus ion, and let's say the amount is P0. So every HCl molecule will give you some dipole moment P0. And let's say we have a collection of these HCl molecules, maybe in the gas or in the liquid phase. But the idea is that let's say we have some container inside, we have a number of HCl gas molecule, right? The idea is that the temperature is not zero, right? Let's say we are working on a finite temperature. So at any temperature which is other than zero, you know the thermal energy, right? So what is the thermal energy? This is nothing but the Boltzmann constant times the temperature, right? That's the amount of thermal energy, and this thermal energy will try to randomize, right, the electric dipole moments. So every arrow in this square box is representing an electric dipole moment, right? And this thermal energy will try to randomize the direction. Direction of all this individual magnetic electric dipole moment, right? And that's why, as the direction is very randomized, the net or the average dipole moment is zero. This is where we don't apply any external electric field, right? The external electric field is absent in this case. And then the net dipole moment. So in this figure, they are denoting this by the P average. So the thermal fluctuation randomize the direction of the individual permanent electric dipole moments, and that's why we don't see any net average or the average electric moment, right? That's zero. But when you place this container, let's say in some electric field along this direction, let's say denoted by this electric field lines, and then all of this, maybe not all of them, because if there are let's say a number of electric dipole moment will try to align in the direction of the electric field, right? But the electric field will try to align all of the moment along the direction of electric field, but it will not be able to do that because there is a thermal energy, right? So it's kind of the interplay between the thermal energy of the system and the energy that's coming from the electric field. So there is a competition in between these two, and as a result of this attempt of alignment due to the external electric field, there will be a net polarization along the direction of the applied electric field. And in that case, the P average will not be zero. So when you apply some electric field, so electric field is not zero anymore, then the sample, let's say, have some average electric dipole moment which is not equal to zero. And this is known as the oriental polarization, because the permanent dipole or permanent dipole molecules trying to align or trying to orient themselves along the direction of the electric field, and thereby giving rise to some sort of average dipole moment, and that's why we call this oriental polarization due to permanent dipole moment. And we need to calculate what is the contribution for this permanent dipole moment inside a solid, right? And let's say these dipoles, right? They consist of, let's say, two atoms, right? Chlorine ions and hydrogen ions, right? So they are really very small structure, right? So when I say that the polarization due to any permanent dipole, right, PD stands for the permanent dipole, is proportional to the electric field felt by the dipole. So again, I want to emphasize the fact that individual dipole will feel a local electric field, right? And that field will produce the polarization. The stronger the electric field, the more the dipole moment will align themselves in the presence of electric field. So that's why there is a proportionality, right? And the proportionality constant here is also known as the polarizability of the permanent dipole moments, right? That's why I put alpha PD. So this is nothing but polarizability of permanent dipoles. And this EPDR is a local field acting on the dipole moment, and we need to know how to calculate the electric field for acting on a local dipole moment. But let's assume for this problem we know the expression for the local dipole moment, then we can find out the individual dipole moment of the permanent dipole, electric dipoles. Now, to understand how do we calculate this thing, let me ask you some questions. Let's say we want to represent all the possible directions, let's say in 1D. So that's a one-dimensional line. So that's our origin. What are the possible direction? Either from origin to right or from origin to left, right? These are the only two possible directions that's possible in 1D. That covers every direction in one dimension. What about 2D? All possible direction. You say, okay, let's draw a circle, and from the center of the circle I will draw all these arrows up to the circumference, right? And this will, and draw all the arrows, many arrows. This will represent all the directions, right, in 2 dimension. So then the question comes, how do you represent all the possible direction in the 3 dimension? So if 2 dimension is covered with a circle, you can imagine that in 3 dimension all the direction has to be in a sphere, right? That's another very important point to remember. So from the center, if you draw different lines to the surface of the sphere, right? So there are, then these are all the direction possible in the 3 dimension, right? The sphere covers all the all the vector starting from the origin of the sphere to the surface represents all the direction that's possible in a 3 dimension, right? Okay. Now I want to introduce another function to you. This is known as the Langevin function, and this function is due to Langevin, who really derived this expression for paramagnetic gas in 1905. So Langevin derived some equation in 1905, and from there we usually call a function in the honor of Langevin. So this Langevin function, let's say L stands for this function, is a function of some argument, let's say A, and this is nothing but cot hyperbolic of the argument minus 1 by A. We will see how this comes about, but for this moment, let's assume we know this Langevin function, and we are trying to plot this function as this Langevin function as a function of the argument A, right? So here we are plotting the values of A, and you can see the Langevin function is this pole line, right? So you can see this is quite linear, where A is really small, right? Here is a linear region, then it's kind of starts bending, and then it saturates at high values, and it becomes, you can see, it's trying to reach the value of 1 at a very high values of A. That's the behavior of the Langevin function. And if somebody asks you, okay, in the very small region of A, right? In this small region of A, what is this slope of this line? This is like almost straight line, and the straight line is as denoted by this A by 3. We will see that how this comes about, right? This will be helpful to understand this permanent dipole electric polarization. Okay, So let's start that how do we calculate the dipole moment for this permanent electric dipole. So let's say we have a piece of sphere, right? And this sphere has a radius of r. So every one of these lines is kind of touching the surface. So from the center, so anywhere, all of these things has a radius of r. And let's say this is a unit sphere, a radius with a sphere with a radius r is equal to 1, right? So unit radius sphere. And this sphere will cover all the direction in 3 dimensions. That's we have already mentioned. So if we don't apply any electric field, the idea is that the permanent electric dipole moments, right, inside the solid will orient themselves in all possible random direction. So they will be covered by the sphere, right? They will be pointing out all the possible direction from the center. So every possible direction is kind of a direction of the electric dipole moment, right? And also, let's say this is our z direction, right? And when you apply some electric field, the dipole moments will try to align, right? Some of them will, but let's try to understand if we apply some electric field along the z direction, right? Because we need to apply the electric field to align the dipoles, and in this discussion, let's the direction of E to be along the z direction, right? E along z axis. That's one thing. Another thing, let's try to understand that this picture that we are kind of drawing an annulus, right? There's an annulus, and you can see the angular width of this annulus is d theta. And what is the radius of this ring on the surface of the sphere? So if this is, you can see that's a right angle. If this is r, right, and then this is r sine theta, right? So the radius of this annulus is nothing but r sine theta, right, which is this bit. But we assume that this is a unit sphere, that's why the radius of the annulus is just sine theta, right, because r is equal to 1. So what is the area of this annulus? That's like the circumference of this annulus times the width. The angular width is d theta. So if somebody asks you what is the area of this annulus, so I'm trying to calculate the area of the annulus is the width of the thing times the length. And what is the length? Length is twice pi r, right? Because that's a circle. So 2 pi r sine theta, right? Because the radius is nothing but r sine theta, but we know in this problem r is 1. So the area of this annulus is 2s pi sine theta d theta, right? That's the from your coordinate geometry. And then you can see that this ring could be anywhere. Let's say if the ring were somewhere here on the equator, right? Then what's the value of theta? 90. Right? And the ring could be somewhere here also. So this ring can be anywhere on the sphere, and the angle will vary from 0 to all the way up to pi, right? Because you can see as you are kind of bring the ring somewhere else, the theta is increasing from, let's say this is the pole, right? And from the pole, it will be, if it is the ring is just a point along the pole, that's 0. And if the ring is somewhere here, let's say, right? Some ring around on the, then the theta will be greater than 90 degree, and then let's say the south pole, on the south pole the point, the theta is just 180, right? So the variation of the theta, that's another important thing. What is the range of theta that will cover the whole sphere? Because the whole sphere is representing all the direction, and we want to cover the whole sphere. That's why, sorry, the theta will have a range from 0 to pi. That's another important thing. These are some geometrical facts reviewed from your second year mathematics courses. And then people generally ask, what is the solid angle extended by this area, right? So the solid angle extended by the annulus. The solid angle is nothing but the area of the annulus divided by the total surface area of the sphere, which is 4 pi r square, and we know r is 1, so this term is just 1. So, and then we have this a factor of 2 here, and the pi goes out. So we have the solid angle extended by the annulus is nothing but half sine theta d theta, right? I think up to now I have made myself clear what I am explaining here. So now and let's say we have all this direction on this annulus, right? So we have this, maybe that's the direction, that's another direction, that's another direction. So on the ring there could be many directions, right? And every one of them has some angle theta with the z-axis. That's another important point to remember. Okay, now let's ask another question, that let's say you have some electric dipole moment denoted by, let's say, some P. So we have some dipole and you place the dipole inside some electric field, let's say some electric field E. So the question is, when you put this dipole moment inside an electric field or of some sort, what is the energy of the dipole moment, right? So that's the energy E of the dipole moment. So let me just be explicit, energy of the dipole moment P. And you know from your electrodynamics courses, this is nothing but minus P dot with the electric field, right? And the minus sign is the convention. So you can see if the electric field is in this direction and all the moments, let's say the P aligns in this direction too. So what is the angle between E and P then? Theta is 0. That's one possibility. And then what about electric field is pointing in this direction and the polarization is pointing along this direction, right? That's another possibility, let's say. For that, theta is 180 degree. So for these two cases, let's say this is case 1 and this is case 2, and you will see that for case 1, let's say for case 1, minus P E cos theta, theta is 0 degree, right? And for case 2, what is the dot product? P and E without the vector sign is just the magnitude of these vectors, right? So you understand this is cos of 180. So you can see for system, for the one configuration where all the moments align or the moment align with the electric field, then the energy of the system is minus PE, and if it's anti-aligned, then that's cos 180 is minus 1, and then there is a minus 1 here, so we have P times E, right? That's a positive PE. So you can see this is lower energy, right? The minus PE is smaller than the plus PE, so alignment gives you smaller energy. So dipole moment will try to align the electric field because it will minimize the energy, right? So any other thing, that's like a maximum energy when it's anti-aligned, and anything in between will be between this range, right? So alignment give you minimum energy. So that's another crucial. So alignment implies energy minimization of the system, right? Energy minimization, right? Okay. Now, so far, we haven't talked about the thing about what is known as like the thermal fluctuation, because in the beginning of the lecture I have mentioned that the permanent dipole moment has some fixed amount of P, but the direction, the vectors inside the solid will randomize because of the thermal energy. And the question is, how do you bring about the discussion of the temperature in the problem? And that's how do you bring the discussion of the temperature? That's through what is known as the Boltzmann factor. This is very standard technique. So that's through the Boltzmann factor, right? And what is this Boltzmann factor? It's nothing but e to the power minus the energy of the system divided by thermal energy of the system, right? So in our problem, what is the energy of the electric dipole moment? That's P times E cos theta. So that's P dot E. P dot E means minus P dot E, right? So minus P dot E divided by kBT. That's the energy of the electric dipole in a electric field. So this minus and this minus becomes a plus. So we have the Boltzmann factor P times the electric field cos theta by kB, right? And you can see in this factor we have this temperature. Okay. And now the question is, what is the quantity that we are trying to calculate, right? So let me go back to this picture. So we are applying some electric field in this direction, and we are asking that all the moments that are randomized, right, on the surface of the sphere, they will try to align. But let's say some of them are lying on this plane, right, on this annulus. The number of, every one of them is making an angle theta, right, of this vector. So what is the contribution? Let's say some vector here has some dipole moment of P along this direction. So the question is, what is the contribution along the z-axis? And that's what we will want to calculate, right? That the contribution of the electric dipole moment of all of the moments along the direction of electric field. So if for this annulus, all the P's are making an angle with theta with the z-axis. So you can see, if somebody asks you what is this contribution along the direction of E for this P's that lying on the annulus, that's like P cos theta, right? This is P cos theta and this is P sin theta. So the contribution is P cos theta. And that's the quantity that we want to trying to calculate, that on the average, because this ring can be anywhere, right? It can be here, it could be here, it could be here. So we need to calculate all the average of this P cos theta term, right? That's the average electric dipole moment along the direction E. Okay, so the idea is that the quantity that we want to calculate is electric dipole moment along z direction average, right? That's the quantity we want to calculate. And how do you calculate the average? Let me give you the formula, right? The average formula is that you need to put down what is the expression of Pz. If it is on the ring, the annulus of that in the picture, you see the P cos theta is the expression for all the moments along lying on the annulus. That's the contribution P cos theta along the field direction, right? So this is the expression, and then we multiply this expression with the solid angle of the annulus. That's, take it as a rule, right? We multiply with the solid angle. What's the solid angle? Nothing but half sin theta d theta, right? That's the solid angle of that annulus. And on that annulus there are many of these electric dipole moments contribution, right? And then you multiply this with the Boltzmann factor. So what is the Boltzmann factor? Pe cos theta by kBt. And then you integrate over the range of theta. What is the range of theta? It starts from 0 to pi, right? That's the numerator or the average. And in the denominator, you have to average only the Boltzmann factor over the solid angle. So this term is absent in the numerator. There is a reason why we do that, but for this lecture, just take it as a rule that the quantity you are trying to average, Pz is P cos theta. The formula is on the numerator. You put the P cos theta, then the solid angle extended by the annulus times the Boltzmann factor. In the denominator, what you have is the solid angle times the Boltzmann factor. Now we should put the integration variable d theta, right? So we have p cos theta by kVt times the integration variable. That's how you calculate the expectation value of electric dipole moment along some direction, right? And we need to calculate these quantities. This half and this half are gone, and we need to calculate the numerator and the denominator, right? So let's write the denominator first. So the denominator, right? I'm abbreviating the denominator as den, and then what we have is in the den is 0 to pi, and then we have sine theta e to the power p e cos theta by kVt, and then we have d theta. So for this integration we will let before that, let's assume we have this term EP times divided by kVt is some variable, some argument or some parameter, the parameter A. So this is nothing but EP by kVt for our convenience. Then we don't have to write it down, the factor many times. So then we can see that we have e to the power A cos theta, okay? So then we will do the variable change that let's assume that x is equal to A cos theta, which we have on the exponent, right? A times cos theta. So from that you can see dx is nothing but minus A sine theta d theta. And for this variable changes, when theta is the upper limit pi, we need to change the limit also, right? So we are changing the limit. When theta is pi, what is the value of x? Cos pi is minus 1, so x is minus A. And for when theta is 0, x is plus A, right? So in this expression, you can see that we have the upper limit is minus A, the lower limit is plus A. We have the minus sign from here, and then we have a 1 by A, because in terms of d theta, sine theta d theta, we have sine theta d theta, that's like dx by minus A. So we are just replacing dx by A, and then e to the power x, right? That's the integration that we need to perform. And this minus sign, let's change the limit of the, through this minus sign we can change the upper limit and the lower limit, exchange them, and we have a factor of A outside, and then so there should be, in the denominator we have x cos theta, and that's A cos theta is just x, right? So we are putting just A here, and if I'm not wrong, that's the integration actually we need to perform, right? Okay, so that's the denominator, and if you perform it, that's easy, right? E to the power A minus e to the power minus A. So once you e to the power x dx is just e to the power x, and then you just put the limit. So on the denominator we have 1 by A and e to the power A minus e to the power A, right? So let's try to calculate the numerator now, right? So in the numerator what we have, so now it's time for the numerator, and in the numerator we have the p, then cos theta e to the power p cos theta by kVt, and then we have the solid angle contribution, right, d theta 0 to pi. The same procedure, we will using the same change of variables. So you can see that we have this A cos theta on the, so we have e to the power x here, and for sine theta d theta we have dx by a as before, right? And also we have this p cos theta, and the value of p cos theta is nothing but the value of cos theta is nothing but x by a, right? So in terms of this cos theta, we can write just x by a, and the upper limit and lower limit will be changed as in the same way as before. So the plus a in the lower limit and the minus a in the upper limit, right? And then from this expression we can use this minus sign to exchange the integration order, right? So upper limit and lower limit can be exchanged, and we have a factor of 1 by a square, and we need to perform the integration e to the power x dx into e to the power x dx, right? So that's the expression for the denominator, and we are performing this integration for the numerator. So let's do that. So we have 1 by a square, and how do you do that? You apply the UV formula, product formula of the integration. So you keep the first function, you differentiate the second function, and you put the limit. That's the first term, right? And then formula has a minus, you integrate, you first differentiate the first term with respect to x, that's 1. You integrate the second function, that's ex again, and then some dx, limit a to a, right? And then if we just put the limit of x here, we have a squared, I'm sorry, that should be a plus and that should be a minus. So we have a times e to the power a, sorry, and then minus, then another plus, because the formula is a minus and there is a minus of a here, that becomes a plus. So a times e to the power minus a, right? That's this term, and then we have this integration, which is nothing but e to the power a minus e to the power a, right? And overall we have this 1 by a square here. So that's our numerator. We have a factor of a which can be brought out, and then so we have 1 by a e to the power, and there's the a square term that cancels this a. So on the numerator we have 1 by a this, and then 1 by a square e to the power a e to the power minus a, right? So we have the expression for the denominator and we have the expression for numerator. So now we can write the expression value of this pz. So I'm missing a p here, right? So just put some p, because there was a p cos theta, and there should be a p, there should be a p, just write the p's. So on the numerator we have this expression, right? P by a e to the power a plus e to the power minus a minus, so this p will be with all of these terms, right? So this is a common term. So then we have p e to the power a minus e to the power minus a by a square, right? There's the a square term here. That's the numerator, and on the denominator we have nothing but 1 by a e to the power a plus e to the power, e to the power a minus e to the power minus a, right? You can see that this a and this a for the first factor is gone. We have this by this, so we have the p times e to the power a plus e to the power minus a divided by e to the power a minus e to the power minus a for the first term, and for the second term the minus and this expression is the same, so you can cancel them. We can cancel this a with one of the a's, right? So you have p by a, okay? And this is, you can see, if you take the p common, we have e to the power a, e to the power minus a, and then e to the power a, e to the power minus a, p to the 1 by a. And this is nothing but our Langevin function that I have discussed, because this expression you can write out using your trigonometric basics, that this is nothing but the cot hyperbolic function. So that's like cot hyperbolic of a minus 1 by a. So the average value of the electric dipole moment along the direction of electric field, which is the z direction, is this formula, right? So we can write it as nothing but the p times the Langevin function. Okay. Now you remember the function has some shape, right? And what's the shape of the function, if you recall? That's 1. The function was plotting as a function of the argument a, and linear, and then it's kind of saturating, right? So there is a region of linear region of the small values of a. So let me find out this linear region, because you can see what is this a. Now we know what is this a. In the substitution, this is nothing but the electric field times the polarization divided by kBt, right? So for high A, electric field is really high. So as we are increasing the electric field, right, what's happening, all the moments will align at some point, right? When LA is 1, then the value in the z direction is p. That means all the moments is already aligned in the electric field. That's really hard, because thermal fluctuation is kind of making the alignment randomized, right? So that's a really high field, which is not really attainable in the experimental situation. But this linear region is of really interest, because there E is kind of small, and then you can apply that electric field in the laboratory easily, right? So this function is just multiplied with this p. So the pz will follow this function, right, multiplied with some number p. So if you understand the Langevin behavior, you understand the pz. So let me find out what is the expression for small values of a, the expression for the Langevin function. So the idea is that the cot hyperbolic a can be expanded in terms of the powers of a. That's like 1 by a, then we have a by 3, then we have some term which is of the order of a cube, right? So series doesn't stop. The next time is a cube, then the term a5, then we have a term like a7. But the thing is, as a is very small, we really neglect all the term that's in the cubic or in the fifth or in the 7th power, right? So this cubic and of the order of cubic terms is kind of neglected. Then we can approximate the cot hyperbolic function for a small a, right? That's a really important thing. For a small a, the cot hyperbolic is nothing but 1 by a plus a by 3, right? And you can see, if you replace this cot function, then the expected value of the pz along p becomes p times 1 by a plus a by 3 for the cot hyperbolic, and there is also a 1 by a term there, right? So this a and this a are cancelled, so we have pa by 3. So the idea is that the average moment along z direction is p by times a by 3. And what is this a? If you recall, a is nothing but e p by kBt, right? We have a factor of 3 here, so that's why. What is this? E is the electric field. Now we have been writing E, right, for a long time, but let me make it clear here in this last step is that you can see we have a p square term here and we have thrice kBt, right? But one important thing, this E actually is really the local field, right? This is difficult to write in all the steps here. That's why But you remember, whatever E we are talking about, that's the local electric field operating on the permanent dipole moment, right? That's the E loc. And from this expression, you can see that our average Pz, which is the expectation value of the average value, is of the form alpha Pd times E loc, right? That means our polarizability for oriental polarization of the permanent dipole moments is nothing but P square by thrice kBt. So if you look at this expression, the take-home message is, for a fixed value of permanent dipole moment P, this thing is inversely proportional to temperature. So if you crank up your temperature of the sample, the polarization will go down, because it's getting difficult to align the moments along the electric field direction, because extra thermal energy is trying to randomize the alignment, right? That's why this is 1 by T. So if T goes up for high temperature, the alpha Pd will go down, right? It's difficult to polarize the material in high temperature applying the same amount of electric field. That's the physical meaning of this expression. And also, it is really difficult to align all the moments, because to saturate this region, the required E field is so high, it's not really possible to align all the moments against this temperature fluctuation, right? So that's how you physically understand the oriental polarization of permanent dipole moments inside a material. I think for this lecture, that's about it, and thanks for listening.